All right, everybody. So we're about to have our plenary for the afternoon session, and I'm very pleased to introduce Anna Weigandt, who you can see is moving right now from MIT to Minnesota, and she'll be telling us about derivatives and Schubert calculus.
Great. Yeah, so thanks so much to the organizers for having me here. It's really exciting. This is my first in-person FPSAC since like 2018, so it's just wonderful to be back here and see all of your faces. So yeah, I'm going to tell a story about derivatives and Schubert calculus. I've listed some collaborators here, Zach Kamaker, Oliver Pachenik, and David Spire. Oh wow. Okay. So, yep, up is back and down is okay. But anyways, so this talk that I'm going to give is based off of projects with various subsets of the people that you see on this slide. Okay. So yeah, it all starts with Schubert polynomials. This is the Schubert calculus part of the talk. So our geometric setting that we're living in is we're looking at this space that's called the complete flag variety. And the fast way for me to tell you what it is it's a quotient of the general linear group by the Borel subgroup of upper triangular matrices. And there's a natural action of this Borel on the flag variety by left multiplication. And with this action comes some orbits. These things are called Schubert cells, and the Schubert cells give rise to the Bruchhaud decomposition of the complete flag variety. If you take the closures of these cells, you get things called Schubert varieties. And the Schubert varieties are really nice. In particular, they're giving us a basis for the cohomology ring of the complete flag variety. So each Schubert variety gives rise to this thing called a Schubert class, and then they form a linear basis of the cohomology ring. So if we want to understand the structure of this ring, what we do is we take two Schubert classes, we multiply them together, and we expand them in the Schubert basis. And we get a bunch of structure constants, these C, U, V, Ws. And for geometric reasons, these are non-negative integers. They're actually counting intersections of certain translated Schubert varieties. So they're positive or non-negative integers, and in special cases we know really nice rules. For instance, most of the people in this room probably know of Littlewood-Richardson rules coming from symmetric function theory. So that's a special case of these coefficients, but in general we don't have an analogous rule that tells us what's going on in the full situation. So in Schubert calculus we're interested in understanding these coefficients in some concrete combinatorial way. Okay, so if you'd rather not do computations in terms of cup products of cohomology classes, thanks to Borel, there's a different way that we can think about this cohomology ring. So there's an isomorphism that takes this ring and maps it to a quotient of just a polynomial ring. So we're quotienting out by the ideal generated by symmetric polynomials with no constant term. And one can ask, well, what's a good polynomial representative for the coset that is the image of the Schubert class? So these Schubert classes were our special basis elements, so of course we want to understand their images under this isomorphism. And one answer for a good polynomial representative is the Schubert polynomials, and they were defined by Lascaux and Schutzenberger. So that's this, this funny math frac S here is a Schubert polynomial, and it's in some alphabet of x variables. So how do we actually write down Schubert polynomials? There's a very concrete way of getting at them algebraically, but it involves a recursive procedure. So we can start with the longest permutation in the symmetric group. That's this W naught, where things are as out of order as possible. So 1 maps to n, 2 maps to n minus 1, and so on. And then we just say, okay, the Schubert polynomial for the longest permutation is just going to be this staircase monomial. And then we get the rest recursively by Newton's divided difference operators. So sometimes you'll see people writing like partials for these. There's going to be derivatives later, so I'm going to write n for Newton. But we take this ni operator takes a polynomial. It subtracts off the copy of the polynomial where we switch xi and xi plus 1, and then we divide by xi minus xi plus 1. And so we take these operators, and the rule is if w, our permutation, has a descent at position I, meaning w of I is bigger than w of I plus 1, then we can get the Schubert polynomial for WSI by applying this divided difference operator to the Schubert polynomial for W. Okay, so just to have some things to look at, this is what's going on for S3. So over here, I've drawn a picture of the weak order on the symmetric group. So these are saying, okay, I multiply by S2 on the right to go down, and that swaps that second and third position. So that's how that works. And then the corresponding Schubert polynomials on the right, we start with this top thing, we work our way down. And you might notice that it doesn't matter which direction we took. We could have gone like this way down in Bruhat order or this way, and we get to the same thing in the end. And that's not just a fluke. These divided difference operators, they satisfy the same braid and commutation relations that the simple reflections do, these SIs which exchange I and I plus 1. So we get a well-defined family of polynomials. Some other features that you might notice, they have non-negative integer coefficients. There's actually a whole lot of combinatorics and ways to write these things down without doing this recursive divided difference procedure, but I'll save that, I think, for later talks this afternoon. We'll get to that. Okay. So one other reason to like Schubert polynomials is that they're a basis for this sort of extension of polynomial rings, so where we take polynomials and as many variables as we want. So what I mean by this is now we don't want to just stick in one particular symmetric group, but we need rather a limit of symmetric groups. So there's a really nice way to just say, well, I'm going to take 1, 3, 2, and think about it as living in S4, so I'm just going to tack a 4 on at the end. And I could think about that as living in S5, just tack a 5 on in the end. So there's this nice stability of permutation groups, and Schubert polynomials respect that stability. When you do this inclusion of permutations, you get the same Schubert polynomial. So you can really think about them as being indexed by elements of S infinity, this group which all but finitely many this group of permutations of positive integers where all but finitely many entries are fixed. Okay. And then again, we have this basis, and one thing that we like to do when we have a basis is we take two things, we multiply them together, we expand out the product in the basis, and we look at these structure constants. And these are the same ones that we were seeing in the flag variety. So if U, V, W are all living in the same symmetric group together, then it's going to be the same coefficient we saw for that flag variety of flags in CN. Okay, so that was the crash course on Schubert calculus. Now let's take some derivatives. So I'm really glad that Zach got to introduce me because this question was really Zach's question. We were in my office one day at Michigan, and Zach said, well, what happens when you take the derivative of a Schubert polynomial? And of course, these are multivariate polynomials, so there's many derivatives one could take. So we just started, taking partial derivatives. So let's just look at an example. Okay, so we started in the Schubert basis, and I've written this out in monomials, and let's go back to Schubert land. So let's write this in the Schubert basis. So we do that, and then if you're like me and you're a combinatorialist, which many of us are, because this is FPSAC, here we have this minus sign, and a minus sign is kind of discouraging and scary, right? Yeah, we don't like minus signs. Okay. Can anyone find a way to make the minus sign go away? Yeah. Yeah, we could just add, yeah, but then we'd have to add another dash here, and I don't want to add that not equal to sign. Okay. So one thing that we could do is we could just add these two things together. If we do that, then, okay, the minus sign goes away. Now we have a nice positive expression. And not only is it a nice positive expression, but there's something really fantastic going on here. So if you look here, we get this permutation by flipping the numbers 1 and 2 in the string. And then we have a coefficient of a 1. Here we could flip the adjacent numbers 3 and 4, adjacent in terms of values, and we get this thing here, and there was a coefficient of a 3 that popped out. And it really just is that simple. The rule is, if you add up all of your partial derivatives and you apply them to a Schubert polynomial, you get a sum over left weak order covers. So just you're looking at all the ways you can multiply by a simple reflection on the left and step down in the left weak Bruhat order. And then whenever you take that step down, you just get a coefficient of a k out front as sort of the price you paid for stepping down. And that's the formula. The proof idea is very simple. It's very elementary. Like, you could give it to your combinatorics students, and I think some of my co-authors have. So the idea is just you show that this operator, oh, I should point out this is a very different nabla from this morning, right? So yeah, this nabla is that. But you can show that nabla commutes with all of the divided difference operators individually, and then you can induct from the top case W naught, where you have a monomial, and monomials are very simple to take derivatives of. Okay, so that's our shiny new tool. I want to point out as well, because a lot of you like Schur polynomials, this rule is very nice in terms of Schur polynomials, which are a special case of Schubert polynomials. Okay, so this is almost certainly review for most people, but just in case, Schur polynomials, they're indexed by partitions, so weakly decreasing sequences of positive integers, and they form a basis for the ring of symmetric polynomials. And people like to study Schur polynomials because they show up in cohomology rings of Grassmannians, they show up in representation theory, and they have just a lot of nice tableau combinatorics to explore. One way that we can write them down is as a sum over semi-standard tableau. So we take our partition, we write down our corresponding Young diagram shape, and then we fill this in with numbers so that along rows we're weakly increasing and along columns we're strictly increasing. And then to each tableau we get a monomial weight by just looking for how many of each different number appeared in our tableau, and this is going to tell us the exponent of the different xi's. So for instance, if we have this partition 3, 1, here's our Schur polynomial that we can write down in 2 variables. We're only allowed to use numbers 1 and 2. If we wanted it in 3 variables, we'd allow ourselves a 3, and so on. So you fix your number of variables, and then you have a polynomial that's symmetric in those variables by this recipe. Okay, so Schur polynomials, I mentioned this, but I just want to give you the explicit recipe. They're actually just Schubert polynomials, and there's a way of translating between partitions and permutations. So given a partition and some number k, which is your number of variables, that's bigger than the number of parts of the partition, there exists some Grassmannian permutation. That means a permutation with a unique descent, so that the Schubert polynomial of that permutation is actually just the Schur polynomial for lambda in k variables. So here's kind of the recipe. If we look at this example, the first thing that we're going to do is we're going to pad out our partition into a longer string so that we match the number of variables that we have. And then we take this thing and we just reverse it. And then we add I to position I for each I. And then now we turn this into a permutation by saying, let's just fill in the missing numbers in increasing order. So I had a 1, 2, 4, 7, and then I'm going to just tack on a 3, 5, 6. If I'm thinking in S infinity, like I could have added an 8, 9, 10, so on, blah, blah, blah. But at this point, really, like we have a well-defined permutation. And the stability means we don't have to care too much about which symmetric group we're living in. Okay, so that's our recipe. Schur polynomials are just Schubert polynomials. And in fact, whenever you have a Grassmannian Schubert polynomial, it is a Schur polynomial. So this is an if and only if sort of statement. Okay, so what does this operator do if we're thinking just in terms of Schur polynomials and we want to think in terms of tableau combinatorics? So when you apply this to a symmetric polynomial, because this is a nice symmetric operator, it stays symmetric. And so what does this look like in terms of tableau? So there's a recipe, which if you know, for instance, the Hooke content formula for writing down the number of semi-standard tableau, this filling should look very familiar. But you put in each box of your partition just the number j minus I plus k, where again, k is the number of variables. So you do this filling like this. And then the rule is just you look at all the different corners of your partition, and you think about removing each of the different corners, and the price you pay to remove that corner is this number that you placed in the box. So this is just a simple translation from the Schubert rule, but it's a very just explicit and nice in terms of symmetric polynomials way of thinking about this. Okay, and so here's just the statement written out formally, and then our example again. All right, so I mention this rule in part because it has its own separate proof. It is a corollary to the other thing. We could derive it very easily, but there's a nice tableau combinatoric sort of proof of this statement. So it depends on jeu de Tacan, which is this sliding game on Tableau. So what you do is you take away some number from your Tableau. It doesn't really matter which number you take away, but I'll just take away this corner for demonstration. And then we want to resolve this thing so it doesn't have a hole and it stays a semi-standard Tableau. So what we can do is we can think about, well, I could either try to slide the 3 into this, but then it would be out of order with the 2, and that would make us unhappy. So instead, I just have to slide the 2 up. And so I do that. And then I look over here, and again, if I tried to slide the 6 there, that would be bad, so instead the 5's going to slide over. And so we just keep sliding and sliding, and now we have this box at this corner. And so we can just take it away, take it out of our object, and we get a Tableau that's still semi-standard that has one less box, and in particular, we got that one less box by removing a corner. So the combinatorial proof of this derivative formula is if you're thinking about this operator nabla, it's really saying, if I think about a monomial as just a string of variables, x1 squared times x2 is really x1, x1, x2. To apply this operator, I'm going to think about taking away each of the variables, in each possible way. At the level of Tableau, that says take a number out of each semi-standard Tableau in all possible ways. And so when we take out those numbers, we get a bunch of holes, which isn't good, but then we can use JDT to resolve the holes. And then what you get, you can show that the multiplicity of each Tableau that you're seeing, so here I'm trying to highlight these ones in particular, matches the number that was in this hook content sort of, hook content formula sort of labeling of our Tableau. So the restriction of this formula to Schur polynomials is very nice. Okay, so upshot, derivatives of Schubert and Schur polynomials are nice. And now the goal for the rest of this talk is going to be to use this formula to understand related combinatorial objects and different situations. Okay, so applications of this formula. There's going to be 3 applications that I'm going to focus in on for this part of the talk. And I'll do it in various levels of detail. It might be a whirlwind, but you can feel free to ask me about any of them afterwards if they pique your interest. Okay, so the first one is Macdonald's identity. So just a reminder, reduced words, every permutation, we can write it as a product of simple transpositions. These simple transpositions are generators for the symmetric group. We could write them very efficiently, or we could write them with some redundancy. An expression is called reduced if it's as short of a factorization of our permutation as possible. And then the number of reflections that we had to use, the length of this factorization is called the Coxeter length of the permutation. And then often we're lazy because who really wants to write all those S's? So instead of writing a reduced expression, we can write a reduced word that just records the indices that we had in that reduced expression. Okay. So Macdonald's identity is this thing here. So it says that if I take 1 over Coxeter length of W factorial, and then multiply that by the sum over reduced words for the permutation, where I take the product of the things in the reduced word, then we get that is the same as plugging in 1s to the Schubert polynomial. So plugging in all 1s and doing that evaluation. So for example, for 2, 4, 1, 3, there's 2 terms in this Schubert polynomial. It also happens to have 2 reduced words. So and Coxeter length happens to match the degree of the Schubert polynomial, so we do this 1/3 factorial. We do this product of the things in the reduced words, we add it up, and then we verify that this thing equals 2. So looking at this, when I learned McDonald's identity for the first time, I was like, why on earth should that be true, that you have these reduced words, and how on earth should you be able to plug in ones to a Schubert polynomial and get this thing? And there were proofs, lots of proofs, but it always just was like a weird formula to me. But once I learned the derivative formula, it became much, much simpler. So the big idea is, well, reduced words correspond to chains in this weak order. So chains from our permutation down to the identity. And then what we can do is we can take derivatives in 2 different ways. So if you have a monic monomial of degree k, and you take this operator to the kth power, you get k factorial. This is something you could ask your Calc 3 students to prove for you. And then our Schubert polynomial, it's homogeneous of degree Coxeter length of w. So when we apply this operator, Coxeter length of w many times, to the Schubert polynomial, we get Coxeter length of w factorial times this specialization. Now we can take the derivative in a different way. We have this formula. And so when we iterate this, what's happening is we're iterating over chains in weak order. In other words, we're iterating over reduced words. And our price to step down at each step was the label of the simple reflection that we stepped down by. And so we really get this Coxeter length of w factorial. Just we took the derivative of the same polynomial in 2 different ways. We apply this operator in 2 different ways, so the things that we get in the end ought to be the same. And so that's just it. Okay, so that was application number 1 of the Schubert formula. And next application is to strongly Sperner posets. So what are these gadgets? So a ranked poset is just a poset that you can sort of neatly arrange, like here I'm drawing pictures of posets, into different rank levels. So there's a consistent way of measuring from a bottom element how many steps you're going up. And I've just conveniently put the rank levels so they're literally on the right levels of this picture. And a ranked poset is Sperner if no antichain, that is a set of incomparable elements, is longer than the largest rank level in the poset. So this thing on the left is Sperner. If we try to find antichains, really, the biggest ones that I can see are just these rank levels. But over here, this one is not Sperner. So for instance, I can take these 2 and these 2, and they're all mutually incomparable. So we have an antichain of size 4, but the largest rank level is size 3. Okay, are you with me? Okay. So that's what it means for a poset to be Sperner. And then strong Sperner is just more Sperner. So what it's saying is that for all k, no union of k antichains is bigger than the union of the largest k rank levels. Okay. So it's some sort of thing that tells us about how big antichains can be in comparison to rank levels in these posets. Now, Stanley developed a really nice way of detecting if posets are strongly Sperner. So what Stanley is saying is if we have this ranked poset where we're decomposing it in terms of its rank levels, suppose that we have this order raising operator. So we're thinking of formal spans of the elements in our poset, so thinking of some formal vector space where our poset elements are a basis. So an order raising operator is just a linear transformation where it takes things from one level to to linear combinations of things in the next level up. And we're only allowed to have non-zero coefficients if there's an honest-to-goodness covering relation in our poset. So it's a linear transformation that carries some information about the poset. So if you happen to have an order raising operator that satisfies this condition that says, well, if we take compositions of this order raising operator, so that if we go from the kth to the m minus kth level, we get a bijection, and this holds for all k in this range, then our poset is strongly Sperner. So the big upshot of this theorem is if we can find this magic raising operator, then we are guaranteed to have a strongly Sperner poset. Here's just like a tiny example. So I've drawn a little Boolean lattice, and then we could just map something to like this linear combination of just things that are above it. So empty could go to 1 plus 2. 1 could go to, 1 and 2 could both go to 1, 2, and so on. Up here, there's nothing for it to map to, so this has to go to 0. And then you'll notice if I square this, I'm taking the empty set to 2 copies of this, and that's fine. That's invertible over Q. So this 1 going from this level to this level, it checks out. It satisfies this condition that Stanley wants it to. OK, so Stanley conjectured in 2017 in this paper some Schubert shenanigans that the weak order on the symmetric group is strongly Sperner. And he showed that it's enough to prove that the determinant of a certain matrix of specialized Schubert polynomials doesn't vanish. And so what this determinant really is it's the special matrix is representing a particular choice of order raising operator, and it's saying, OK, we have our compositions, we want to check that we have an invertible linear transformation. It boils down to computing this determinant. And Stanley actually gave like conjectural formulas for these determinants. So if you could prove that Stanley's formulas were right, then it was clear that the determinants didn't vanish, and so it was clear that you have the invertible linear transformations that you want. So you can prove this determinant formula by looking at really just the derivative formula. And the key thing from the derivative formula is that on the one hand, if you're thinking in terms of Schubert polynomials, it's like thinking in terms of permutations. And so you're climbing. So we have to maybe flip our poset upside down, whatever, we'll brush that under the rug. But we're climbing in our poset. And it might be hard to think about these covers, but we have this convenience that we can change basis. And we can think in terms of monomials instead. And so we can use this going back and forth between permutation basis and monomial basis to get at some extra structure in a similar way to what we did for this McDonald identity proof. So I should also mention that Gates and Gao, they proved that the weak order is strongly Sperner. They gave a separate proof, but didn't address this determinant question, they didn't look into the determinant. OK. So yeah, and then the third application that I want to get to is special rules for Schubert structure constants. So remember, we can multiply 2 Schubert polynomials, we can expand them out in the Schubert basis, and we want to understand these coefficients. Okay, so yeah, what we can do is we can leverage the product rule, because we have a differential operator, this satisfies the product rule. So here, I have a bunch of linear relations of coefficients. You should really read the proof idea first and then the theorem. So that's what we'll do. So we can take the product of 2 Schubert polynomials, expand them out in the Schubert basis. And then we can apply this operator to both sides. So on the left-hand side, we literally just get product rule. On the right-hand side, by linearity, this thing just kind of pops past the sum and goes, and we apply it to each of these individual Schubert polynomials indexed by z's. And then when we apply the formula for nabla, then what we get is just a whole big mess of a bunch of stuff with a bunch of i's, j's, and k's floating around. But when we extract the coefficient of the Schubert polynomial for w from both sides, this is what we get in the end. And so we have a basis, we have a coefficient on the left-hand side, it better equal the coefficient on the right-hand side. Okay, so this formula, there's too many terms, just way too many terms. So what we can do is we can think about this special case where there are less terms, and less terms is great. So the easiest case is when U and V are both permutations that are inverse of Grassmannian permutations. Another way to say that is that they each have a unique left descent. So in this case, that big, scary-looking formula, it just has 2 terms on the left-hand side, which is great. And then on the right-hand side, there's still a bunch of stuff potentially, but maybe we could hope to make sense of it. And then by like stabilization tricks, which I'll sweep under the rug, we can drop coefficients from this formula at the price of picking up an extra Schubert structure constant. Okay. So the we is me and Oliver Pechenik. We extended a rule of Weiser in terms of PQ clans to understand what's going on the right-hand side of these expressions. So we changed PQ clans to something we called back-stable clans, and we were able to understand the right-hand side, which gives us hope of understanding the left-hand side. So what do these clan rules look like? Again, this could be its own talk, so I'm going to just show you the cartoon. But the big picture idea is that each each pair of inverse Grassmannian permutations corresponds to a back-stable PQ clan. So this is a partial matching, really, of like all integers, but eventually we just get like things matched up in a nice sort of stable way. So we just look at this little window, we do a partial matching, and then there's some things that didn't get matched up. They get pluses or minuses. So there's a particular construction that takes this pair to a particular starting PQ clan. And then we apply these little local moves which take this thing and they try to bring it closer to this nice form here. This is what we call the rainbow clan. And we call it rainbow because it literally, like, it's as nested as possible, and there's maybe some signs in the middle, but it looks like a rainbow. And then these little moves, they do little local swaps. So for instance, this T1, it says, well, we want to try to get this to be more nested, so let's let this one pass past the two. And so these start to cross. This T0, we say, oh, it's a shame that these are crossing instead of nesting, so let's make this so that they're now nesting. This T2 here says, oh, we really want this sign to be in the middle, so let's let it pass. So there's a whole zoo of these little local swaps, but some very concrete procedure. And we look at all the different legal ways of starting from the starting clan and getting to the rainbow clan. And then this rule says that the Schubert structure constant, Cu v W, is 1 if there's a word for W, a reduced word from the top clan to the bottom clan, and then it's going to be 0 otherwise. So for example, we have this word. Here we really want W to live in the positive symmetric group, so it can't have any zeros. But we have like this T1, T2, T3 path would give us this permutation here. Which C? Oh, yeah. I was trying to sweep the C under the rug. It's a particular Schubert structure constant that we get by doing like 1 cross U and 1 cross V and then an S1 of 1 cross W. So it's just like a little technical thing. Basically, the idea is when you stabilize in that way, structure constants don't change, and we can use that to get a formula where now instead of P and Q, we have P plus 1, Q plus 1, and then we can just do baby linear algebra to get these coefficients to drop. Okay. And then, so great, we now understand the right-hand side. And in particular, that was a good point. This does fall within these clan rule sort of situations. So we understand the right-hand side. And then here we have now 2 unknowns in 2 linear equations. Most of the time, they're linearly independent if P is not equal to Q. If P does equal to Q, well, we can work a little bit harder and then everything's fine. But the point is we can solve for what these coefficients should be and understand them very explicitly through the same type of clan combinatorics. And we were really able to see this by using just like the product rule and derivatives. So one could ask, can we iterate this more? Can we get more clan rules for more things? Okay, so that was Schubert land. And now in the remaining time, I want to take derivatives of one of my other favorite families of polynomials, which are Grothendieck polynomials. Okay, so what are Grothendieck polynomials? They're coming from K-theory of flag varieties now, so we're moving from cohomology to K-theory. And they're defined in a very similar way to Schubert polynomials. In fact, the Grothendieck polynomial, this is mathfrak G, for W naught, it is just the same as the Schubert polynomial, so the same initial condition, but now we have more funny looking operators. So I'm going to define this ni bar of f to be the result of applying ni to 1 minus xi plus 1f. Okay, so notice this operator is no longer like a homogeneous sort of thing. We have this xi boosting the degree up. We have a minus sign, so we might get cancellations going on. So this is just like a wilder operator. But it's the same sort of rule. If w has a descent at position I, then we can get the Grothendieck polynomial for wsi by applying this operator ni to the Grothendieck polynomial for w. So just so that we have a picture to look at, most of these Grothendieck polynomials are actually just Schubert polynomials. So S3 is a little small to really be noting good features. But we can see this one right here has some interesting stuff. So the Schubert polynomial before was just x1 plus x2, but now we have this extra minus x1, x2. So some features to notice: the lowest degree terms of Grothendieck polynomials are always Schubert polynomials. The signs alternate with degree. So there are minus signs, which could be terrifying, but it's okay because it's controllable negativity. We have this alternating with sign, so that's fine. There's, again, lots of nice combinatorial formulas to help us write down Grothendieck polynomials that allow us to skip this divided difference operator sort of perspective and just write them down in terms of combinatorics. But we always get, integer coefficients that are alternating in sign with degree. Okay, so and I wanted to take derivatives of Grothendieck polynomials because you could do it for Schubert, so why not Grothendieck's? So now these polynomials, the formula, it looks a little bit more involved. The right-hand side looks basically the same. So we're still summing over these left weak order covers and paying a price of k to do that. But then on the left-hand side, we have this nabla operator. We also have this extra operator e, which is going to be a sum of the partial derivatives, but we're going to multiply by xi in front of each of the partial derivatives. Okay. And then here, this is this major index of the inverse permutation. So just explicitly what this looks like is we're summing over left descents of w. We're summing over the positions of those left descents. Okay, so this is the formula. Notice E, what that does really morally is if you plug a monomial into this thing, it spits out a copy of that monomial, but then with a coefficient that was the degree of the monomial. So it looks all scary, but it's not scary. It's just doing that to monomials. Okay. So yeah, we have a new tool, we want a new application, and this got us thinking about this thing coming from commutative algebra called Castanova-Mumford regularity. Okay, so this again could be a whole different talk, so I'm not going to really define this rigorously for you or at all for you, but I'm going to just tell you like broadly what it is. So Castanova-Mumford regularity, it's an invariant coming from commutative algebra that tells you how complicated minimal free resolutions of graded modules can be. So in particular, one might care about regularity if you want to do computations that tell you things about modules. So maybe you want to find Grosvenor bases, maybe you want to compute free resolutions. If you happen to know the regularity, you can tell the computer you don't have to work that hard. You can just like stop at this point, and it can speed up computations for you. So it can help you discover more information about the module a lot faster. Now, Jenna Ratchcott observed that if you happen to have a Cohen-Macaulay module, then the regularity is just the difference between the degree of this gadget called the K polynomial and the height of the ideal. Or really, you can think about the codimension of the vanishing of R mod I. So what this K polynomial is you can take the Hilbert series, which records the dimensions of different graded pieces of your graded module, and then you can sort of divide by some standard denominator, and you magically get a polynomial up top, and that thing is the K polynomial. Now, for us, I'm going to just like spoil another slide. Okay, so the modules that I like to study are things called Schubert determinantal ideals. So these are generalizations of classical determinantal ideals. So these ideals that are minors of a fixed size in some generic matrix. Schubert determinantal ideals are, again, generated by certain minors that are determined by the combinatorics of the permutation. So for instance, the determinantal ideal for 2, 1, 4, 3, we have just this like 1 by 1 minor here, and then we have this 3 by 3 minor here are generating this ideal. So again, I'm not going to give you like the full recipe, but there's a very explicit combinatorial recipe to write down the generating sets of these gadgets. Now, Fulton showed that the height of the Schubert determinantal ideal is just the Coxeter length of the corresponding permutation, and that R mod IW is Cohen-Macaulay, which is great. So we're exactly in this nice situation where Jenna said it's enough for us to find the degree of the K polynomial. Okay, so what is this K polynomial? Well, the K polynomial is just obtained by specializing for each xi 1 minus t into the Grothendieck polynomial. And this change of variables, because of this alternating in sign sort of property, is degree preserving. So we're never going to like knock stuff out of the top degree. We just stay the same. So the upshot is we really just need to understand the degree of the Grothendieck polynomial. And the good news is like we have years and years of combinatorics to help us think about Grothendieck polynomials. Now, when I ask like what's the degree of the Grothendieck polynomial, you could say something like, oh, there's a pipe dream formula and look for the pipe dream with the most number of crossings. And that is like an answer, but it's not a very satisfying answer. So really, to answer this question, we wanted to avoid like recursive algorithmic constructions if at all possible, and just find a simple statistic on permutations. Okay, so yeah. Now, where are the derivatives? Well, if we want to think about degrees of Grothendieck polynomials, we can think about what's going on inside of this derivative formula. So in particular, if we start staring at this derivative formula, and we want to know when is the degree going to drop, that happens precisely when we have that the major index of W inverse is the same as the degree of the Grothendieck polynomial for W. And so when that happens, these two pieces will cancel. On the left-hand side, we'll just have derivatives, which are naturally going to make degrees drop. And then that tells us when we're in this situation, the degree of this Grothendieck polynomial is strictly bigger than the degree of anything that it's covering. So we can extract degree information from this derivative formula. And this led us to start thinking about like when in particular are like what permutations are having this special property where this major index of W inverse is equal to the degree of GW. So, and the answer is just these things called fireworks permutations. So I think this is like David's terminology. So fireworks is, the definition of a fireworks permutation is if you look at the initial elements of its decreasing runs, they're in increasing order. So for instance, here I've separated out the decreasing runs of this permutation. And then here, this initial thing, we have a 4, we have a 6, we have an 8, we have a 9. And this is really like in any good fireworks show, if you're like shooting up a firework, it's gonna like go up and then it's gonna fall a little bit, right? And then maybe you want the next one to go higher. So it goes up, it explodes, it goes down. And so a good fireworks show, everything should have a bigger peak than the previous thing. It should just keep building and building. So that's the reason for the terminology. Now, another characterization is that these are the permutations that are 3-1-2 pattern avoiding. So this means that this 3-1-2 pattern, the 1 and the 2 piece are consecutive. So the theorem is that the degree of the Grothendieck polynomial equals the major index of W inverse if and only if W inverse is fire. It works, so we can pick this out. It's fire. That's like, it's lit, yo? Not Gen Z. I'm a millennial. Okay. So, Yeah, and that's like one way of looking at this. And then we really, again, want a concrete permutation statistic that's going to help us out in computing degrees. And so in thinking about these fireworks permutations, we were led to find like the right construction that really works for all permutations. So the way the statistic goes, it's better for me to just show you than tell you. So we start by writing a bunch of truncations of our permutation in a nice little array like this. So we write the permutation, then we throw away the first entry, then we throw away the next entry, and so on. And then in each line, we look for longest increasing subsequences that start at the first position. That's a mouthful. So what are we doing? Like here, I'm going to start with 7. And then I want an increasing subsequence of this string that starts with 7 and is as big as possible. Well, the only thing bigger than 7 is 8. So I'm going to like box up that sequence. And then like this next line, we have to start with 1. We could do like 1, 6, 8, but that would be kind of shorter than 1, 4, 5, 8. So like this is a longest increasing subsequence. And we continue on in this way in each row. And we get some sort of like a bunch of boxed entries that are corresponding to our increasing subsequence. And then the Ratchcott statistic is we just count how many things in this array didn't get boxed. So if you count, hopefully it's 19. But this Ratchcott statistic is the number of unboxed entries. Okay. So the theorem is that if we have W in Sn, the degree of the growth-unique polynomial is this Ratchcott statistic. And then in particular, we wanted to find this Castanova-Mumford regularity. This is just this statistic minus the Coxeter length. So here's just a tiny example with W being 1, 3, 2. We have this growth-unique polynomial. It's degree 2. And then we could play this game. We get 2 uncircled things, which matches that, which is great. OK, so that was kind of a whirlwind tour of derivatives of some of my favorite polynomials. And I just want to leave you with one main takeaway, which hopefully you can take to whatever your favorite family of polynomials is. And it's that differential operators are really useful for extracting structure from combinatorial families of polynomials. So you might want to think about how you can use operators and different tricks to understand your favorite combinatorial things. So with that, I'll go ahead and stop, and thank you.
Thank you, Anna, for that wonderful talk. I see we have a lot of questions. I'm going to start with Dominic.
Have you tried applying differential operators to other families? Like the key polynomials seem like a natural next step.
Yeah. So the question is, have I tried applying operators to other families, in particular key polynomials? I think I've tried key polynomials. I don't want to say one can't do key polynomials. I couldn't in 2018, but maybe one could now if one tried harder. Yeah.
Is there some like geometric thing that like when you did the nabla applied to a Schubert and it was a positive sum of Schuberts, is that there's some like geometric interpretation of what the nabla is doing on a Schubert variety?
Yeah, so Maria was asking, is there a geometric interpretation of what this nabla operator is doing? Yeah, I would love it if there was. I don't know one, but for instance, like Schubert polynomials are multi-degrees of matrix Schubert varieties. Is there something weird that you could do to a matrix Schubert variety or a Schubert variety and get that? I don't know, but that would be awesome. Yes, Steve?
What's the most efficient way to compute the Ratchcott statistic of a permutation?
Yeah, so what's the most efficient way to compute the Ratchcott statistic of a permutation? I wish that, maybe I could like punt this out to Aya actually. I don't know where you are, but there was just a lovely.
Putting it in the matrix Schubert package.
Yeah. Yeah.
It will appear in the fall probably.
Yeah, so at Minnesota, they just had a nice Macaulay 2 workshop where they implemented a bunch of things about matrix Schubert varieties and regularity. And Tricia Klein was doing like software demonstrations at the Schubert Calculus Conference in Illinois and showed that it's really fast to compute this statistic. Oh, maybe David has a...
Well, you could use the obvious following a definition where you have 4 squared.
Yeah, I think like initially when I brought the derivative formula, oh sorry, there's a Q analog for McDonald. Can you get that with derivatives? So I think I was like hoping that Grothendieck's would somehow help with that, and that's how I started like talking with David and Oliver about like. But then we like veered towards regularity and away from McDonald-y things. But it would be interesting what sort of formulas you can get. It kind of, one difficulty is that the McDonald formula for like Schubert's, you just get down to a constant. The formula with Grothendieck's, you always have like leftover stuff that you have to like deal with somehow, but maybe one could. Yeah.
So from what I understand, if you just try to do the kin and call in the middle of a tableau, it's not usually confluent. Do you have a specific choreography in mind, which ones you start with?
Oh, so if you do JDT in the middle of a tableau, it's not usually
Or maybe it's about several holes?
Yeah, if it's just one hole, there's like only one thing you can do, right? Because like one's going to be out of order with the other. So I think you're safe with one. Yeah.
There is a version of JDT for complex spectrum, so can we use that to see the derivative formula like in the corresponding table?
Yeah, so I would ask like Hugh Denon, I think, has, oh, sorry. So there's a version of JDT for bumpless pipe dreams. Can you use this to understand? So yeah, I would, I think Hugh Denon is like actively working on additional combinatorial proofs for the general Schubert case.
Have you tried anything with the Laplacian operator?
My answer, have I tried anything with the Laplacian operator? My answer is probably no, or not recently, or I was unsuccessful, but yeah. Not that, again, all of this is like, there's so many things one could try, and like, yeah, I would say just because I've said like, oh, I might have tried it, like someone else should try it. Yeah.
So my impression is this doesn't work in other Lie types. Do you have any interpretation of why?
Yeah, so your impression is this doesn't work in other Lie types. Any wondering why? This is another one where I should say like we tried other Lie types. We weren't initially successful, but there's not a reason that one couldn't be successful with more elbow grease. Yeah.
Do you have sort of an explanation for the Grothendieck's why it looks like just the GLN's sum of the diagonal entries acting that E operator?
So I'm not.
Grothendieck case.
I'm not fully understand or parsing the question. Maybe I should like ask you about it. Ask you about your question later. Yeah. Yeah. Have I tried integrating Schubert polynomials? Yes, I have, and I don't know. I forget why I didn't like integrating Schubert polynomials. Maybe this is another one where I like tried it and wasn't very successful, but one could be. But yeah, it just like it gets a little bit weird because you have to decide like how many variables you're using and to go up. And I don't know if it was particularly nice or maybe not even Schubert positive or something. There was some sort of obstruction that I didn't like, and then I turned another direction.
If there are no further questions, let's thank Anna again.